So thank you very much for the introduction and for the invitation. Of course, I would have loved to travel to Spain, but that's not possible. And I really appreciate the organizers' effort to hold this meeting online. It's really pleasant for me. So, okay, yeah, today I will talk about hyperbolic planes in Minkowski space of dimension 3. Everything will be based on joint work with Francesco Bonsante and Peter Smiley. So I start by more or less introducing the objects and the problem. Of course, everyone here knows what the Minkowski space is. The purpose of this talk is to study surfaces of, let's say, constant or some results also bounded curvature and negative curvature in Minkowski space. We'll talk about space-like surfaces. So the induced metric is a Riemannian surface, and we consider surfaces of constant or sometimes bounded. Everyone here knows also an example of this. There's just the hyperboloid in Minkowski space. So the set of points at distance, Minkowski distance 1 minus 1 from the origin in the future. Here is a picture. Everyone has seen this picture before. The blue cone is just the light cone from the origin, and the red is the hyperboloid, which is actually a copy, a model of the hyperbolic plane. So hyperbolic plane is basically up to isometries, the unique, simply connected Riemannian surfaces, which is complete and has constant curvature -1. And this is one of the models. Hano and Umizu in 83 found some examples of other copies of H2 into Minkowski tree space. So some isometric embeddings of H2 into M3, which are not equivalent to the hyperboloid. So the induced metric is the same, but of course the extrinsic geometry is different. In fact, they didn't just found some sporadic examples, they produced a one-parameter family of examples. And here I will picture some of these examples. So here, this is just the usual hyperboloid, the one I've shown before. This one might seem very similar, but it's not the same. It's a little thinner somehow in the left and right direction. And then we have another one which is somehow the opposite. It's fatter in the left and right direction and sort of thinner in the transverse direction that you don't see from the screen. And in fact, there is an entire one-parameter family of these examples that interpolates from the hyperboloid and these other surfaces. And there are also some sort of limits. So these are pictured in a very symmetric way, but there are some limits of these surfaces like this. So imagine that you let these surfaces become fatter and fatter, but at the same time we translate a lot. Then in the limit we get another surface of constant curvature -1. I'll come back to these examples of Hano and Umizu later on to explain how they have acted. But before that, I would like to make a sort of intermezzo and discuss the differences with respect to Euclidean geometry. So just this slide will be a sort of comparison with the situation in Euclidean geometry. So what do I mean with the situation in Euclidean geometry? Well, there is a famous theorem of Liebman that has then been reproved and refined by Hilbert that says that whenever you have a compact surface in Euclidean tree space that has constant positive curvature, then it is a round sphere. And you can even replace compact by complete here because, okay. Anyway. So there is a lot of rigidity in the Euclidean setting. Basically, what this means is that these deformations that we saw from the Hano and Umizu examples, which are deformations of the imaginary unit sphere in Minkowski space, are not possible in Euclidean geometry, strong rigidity. But however, so the sphere cannot be deformed in such a way that it keeps positive constant curvature unless you deform trivially just by translating. But I would like to stress here that this theorem of Liebman has a global character. So one can find deformations of portions of a round sphere which still have constant curvature 1. The deformation fails once one tries to do it globally. So here I will show you in fact, one way to produce this deformation just by surfaces of revolution. So this is a one-parameter family, very similar to the Hahn-Minkowski example. Somehow the Euclidean cousins of the Hahn-Minkowski examples. So that's basically one-parameter family of examples. These are surfaces of constant curvature plus one, surfaces of revolution. You see in the middle of this movie, you see the sphere, and then these are other surfaces. So basically, this is to say that you can produce some local deformations. For instance, this lemon-shaped surface. So it's pictured in yellow, not because it's a lemon, but it's not a hyperbolic plane in Minkowski space. So it's not red as the other ones. This is yellow because it's something else. The feature of this surface is that they have constant curvature 1. So locally, they're isometric to a round sphere, but not globally. So basically, there are these two singular points. So this is why this does not contradict the Lyman theorem, because this is topologically a sphere, but it's not a smoothly embedded sphere. So after this remark on Euclidean rigidity, let's go back to the Ano and Umezu examples. So the examples produced by Ano and Umezu are somehow constructed in a similar way. So there are surfaces of revolution, but now with a space-like axis, meaning that we take a one-parameter family of isometries of Minkowski space, which fixes a horizontal, let's say the x-axis. And what you get is a surface like that. That's the surface that I've shown before, the red one. Then there is this blue region, which, if you know what it is, this is the domain of dependence of the surface, but I come back to this later. So for the moment, you can just focus on the red surface. You see that this surface contains some hyperbolas in the same way as surfaces of revolution Euclidean space are foliated by spheres. And basically, if you try to look for a surface of revolution of this form that has constant curvature -1, then the problem becomes an ODE. And it's a very, very simple ODE, an ODE that every undergraduate can solve, like x double dot is equal to x. And you can also, let's say, this is a little more complicated, but a very advanced undergraduate, let's say, can also compute the induced metric. So basically, you can show that if you take maximal solutions of this ODE, then the induced metric is a complete metric of constant curvature -1. It's simply connected. So this surface of revolution is globally isometric to H2. It's really an isometrically embedded copy of the hyperbolic plane. Is everyone still there? No.
Yes, we're here.
Okay, good. Sorry, but it was a very bad.
You can ask whenever you want.
Yeah. Okay, so this is about the Ano and Umezu examples. I also would like to spend one slide on another large class of examples, which is not completely fundamental for for the results I'm going to present, but I like this construction a lot. So Barbeau, Begin, and Ganidze-Gibb in 2006 provided a result which gives many other examples of isometrically embedded copies of H2 in Minkowski tree space. The way they did this is the following. Basically, they considered a Fuchsian group in SO21. So here I'm considering SO21 as the isometry group, the group of linear isometries of Minkowski space. They consider a Fuchsian group, meaning a group that acts on H2, let's say on the hyperboloid, by isometries with compact quotient. And there are many such groups. Basically, they are parametrized up to conjugation by the Teichmüller space, which is a real manifold of dimension 6G minus 6, where G is the genus of the quotient surface. A rough dimension count shows that the dimension is 6G minus 6, because if the quotient has genus G, then your group has a presentation with 2G generators and one relation. And this group has dimension 3, the SO1 has dimension 3. So basically you have, for each generator, you have 3 degrees of freedom, so you get 6G dimensions, but then you kill 3 because you have one relation to be satisfied, and you kill other 3 because you mod out by their equivalence relation two groups which are conjugated are identified. And then what they consider is an affine deformation of gamma. So basically what this means is that they took this group gamma and they added a translation part. And the same dimension count, roughly, tells you that once you fix gamma, then you have 6G minus 6, a real vector of dimension 6G minus 6 of such affine deformations up to conjugation. So in total, we have 12G minus 12 parameters. And they proved that for every affine deformation of gamma, there exists a unique surface which has constant curvature minus 1, and it is invariant by the action of this affine deformation of gamma. So the quotient is hyperbolic surface, and basically, since the universal cover of any closed hyperbolic surface is H2, these invariant surfaces give many other examples of hyperbolic planes in Minkowski tree space. And of course, if the translation part is trivial, then this is just a hyperboloid. Otherwise, all the surfaces are non-equivalent. Any questions so far?
No, there seems that there is no question.
Good. Sorry. Yeah, so at some point, it's very natural to ask the following question. We would like to classify all the isometrically embedded hyperbolic planes in Minkowski tree space. So that's the question that I want to somehow address today. Basically, we want to classify all isometrically embedded hyperbolic planes. And it's a very natural question, very simple to state, but somehow surprisingly, this is an open question at the moment. I will present some results, but before that, I want to settle some facts which are sort of relevant for what's coming. So the first fact, it's very easy to prove, is that whenever you have a complete space, like of course surface in Minkowski space, then it is entire. Entire just means that it is an entire graph. It's a graph of a function defined over a plane. Of course, you can say something about this function. So since our surface is supposed to be space-like, our function, which is smooth, let's say, is a one Lipschitz function. And also, the surfaces that we consider have a constant curvature -1. So by the Gauss equation, the determinant of the shape operator is 1. So these surfaces are either convex or concave. And up to applying a reflection, we will always assume that our surfaces are convex. And we will make this assumption always in this talk. But the important thing is that the converse is not old. So it's not true that an entire space-like surface is complete. That's very important for the purpose of this talk. And one can construct also counterexamples which have curvature -1. And one way to construct this counterexample is to consider, again, a surface of revolution, so a sort of invariant surface by a one-parameter group, but now the fixed axis is lifelike. And I'm going to show you a picture. So basically, this is the surface that I'm going to present. This is invariant by a parabolic group, which fixes this direction. Basically, the reason why this thing can happen, why an entire surface has the right not to be complete, is that you can imagine that although this surface is properly embedded, it approaches a null direction very, very quickly, so that you can have some geodesics of finite length that escape compact sets and approach very, very quickly this light-like direction. I'm also going to show you a movie of the surface. So you see on one side, the surface looks very much like a hyperboloid, but here the surface is approaching a null plane very, very quickly. So on this side, basically here we are approaching a null direction very quickly, and that's the reason for incompleteness. Although this surface is a Riemannian surface and it's properly embedded. So in fact, this example is also very easy to manage, and one can prove that intrinsically the surface, as I said, is incomplete, and intrinsically it is isometric to a half plane in H2. So basically, we have finite length geodesics which get these boundary components, and these are the geodesics that are escaping in this direction. So that's one of the main difficulties of classifying hyperbolic planes in H2. It's not the same as classifying entire surfaces. So let's, for the moment, take one step back. And any question on this?
No questions.
Okay. Most of the time I ask if there are questions just to make sure that everyone is still there.
I know.
So let's take one step back and let's try to classify entire surfaces. So now in this slide and the next ones, I will give you a classification. In this case, we know what is the classification of all convex entire surfaces that have constant curvature -1. These are not necessarily hyperbolic planes, but still hyperbolic surfaces. Basically, to give this classification, I had to give you a sort of classifying object. And this goes through the notion of the Legendre transformation. So basically, when you have a surface, a convex surface, which is the graph, an entire graph, let's say, you can define, this is standard in convex analysis, you define the Legendre transformation, which has this formula. It's a real function that can also take the value +infinity because it's a supremum. You don't have to focus too much on this formula right now, so you can also forget what's written there. I will give you an interpretation later on. But standard facts in convex analysis tell you that since our initial function f is Lipschitz, this sort of dual function is finite, so the set on which it's finite is contained in the closed unit disk. And our classifying object is the null support function, which is the restriction of this Legendre transformation to the boundary of the disk. You don't have to concentrate too much. Next slide, I will picture what this means. What's the geometric interpretation of, what the geometric interpretation of this null support function is. But this is the classifying object. So it's a function that is defined on the circle, and it is real or +infinity valued. And the classification theorem for entire surfaces is the following. Basically, we have a bijection from the set of all entire hyperbolic surfaces, let's say convex, I'm always assuming convex here, and the set of functions on the circle with values r or +infinity, which are lower semi-continuous and finite on at least 3 points. And this bijection is just taking a surface and associating the null support function. So this result contains many statements. So for instance, the first thing is that the null support function is necessarily lower semi-continuous. That's very easy because it is a supremum of continuous function, and it has to be finite on at least 3 points on the circle. And then there is the existence problem. So one has to show that for any such phi, you can find such an entire hyperbolic surface. But anyway, this is a classification result for entire hyperbolic surfaces. By hyperbolic, I mean just the intrinsic curvature is -1. Now I want to give you a geometric interpretation of this null support function. So here is just a pictorial interpretation. So this is our surface sigma, okay? It's a convex surface, space-like. We want to associate to this surface a function which is defined on the circle. So let's pick one point on the circle. To this point on the circle, we have a light-like direction, which is, let's say, projects down to the light-like geodesic, which projects down to the ray from the origin through P. Can you see this picture? It's fine?
Yes, perfect.
So we want to define the null support function for this point P. So we have this light direction determined by P. There is also a light plane which contains this null direction, which is uniquely determined by P going through the origin. This light plane has no reason to be asymptotic to our surface. Of course, if our surface is just a hyperboloid, then the light plane will be asymptotic, but in general it will not. But we can try to translate this light plane, and if we are lucky, we find a certain amount such that this translated plane becomes asymptotic to the surface. And the amount by which we translate it vertically is minus the null support function. So this is the geometric interpretation of the null support function. This null support function can be plus infinity. This means that regardless of how much we translate vertically, the translated planes will always intersect the surface. That's possible, of course. So this is why this null support function is allowed to take plus infinity as a value. And also, a side remark is that the null support function uniquely determines the domain of dependence of the surface. So domain of dependence of a surface in Minkowski space is the set of points such that every inextensible future time-like curve from that point intersects the surface. And basically, one recovers the domain of dependence just as the intersection of all the half spaces bounded by light-like planes, which are determined by the null support function. So you take this construction in the converse direction. You take all these null planes determined by phi sigma. You take the upper part and you intersect and you recover domain of dependence. And here I give you some examples. Well, if the surface is just hyperboloid, then domain of dependence is the future come from the origin. And in this case, the null support function is just constant. It's just 0 because basically the surface is asymptotic to the light core. That's the reason. This example that I pictured from Ano and Umizu, I told you before that the blue thing is the domain of dependence. In this case, the null support function is something like that. It's piecewise affine. And this other example, which is yellow because it's not a hyperbolic plane, in this case, the null support function has a jump. So this point here is basically the direction in which to which finite length geodesic converge. So this jump here is basically the reason why this surface is incomplete. And I want to try to make this formal in the last part of the talk. Everything clear so far? Some questions on these examples?
No, I think it's clear.
Okay. I feel relieved every time you provide an answer to my questions. So now I want to present the results. So basically now the question, remember that the original question was to sort of classify isometrical embedded hyperbolic planes in H2. And this is not equivalent to classifying entire surfaces. So basically, to answer this question, we must understand what is the condition on this null support function phi sigma, which corresponds to complete surfaces. We've seen that every lower semi-continuous function finite on 3 points correspond to an entire space, like surface of curvature -1. The question is, when is it complete? And we don't have a complete answer. Sorry we don't have a full answer, but we have some conditions. So suppose sigma is an entire surface, it has constant curvature -1. Then if the following condition holds, then our surface is complete. How shall we read this condition? Basically, pick any point on the circle. This condition is saying that we can find a sequence, okay? We can find a sequence approaching P on which basically null support function is sublinear, basically, for some constant C, okay? Remember that our null support function phi sigma can also be infinity on large portions, but nevertheless, if there is a sequence on which it's sublinear and the sequence is approaching P, then our surface is complete. This is not sharp, it's not an if and only if, but we have some other implication. So basically, if the surface is complete, then we have the following condition. Again, for every point on the circle, we can find a sequence approaching P on which the function is not sublinear, but it's almost. So basically, we just add an exponent alpha here. And we can prescribe any alpha and any C. So the condition is pick any point on the circle, pick any exponent alpha in 0, 1, pick any constant. Then we can find sequence approaching P on which the null support function is less than Cx to the alpha, basically. So you see there's a gap from here to here, not a huge one, because here we have alpha equal to 1, and here alpha between 0 and 1, so there's still a gap, but it's much thinner than we thought before. And just a side remark that these results, in fact, do not quite assume that the curvature is constant. It suffices that the curvature is negative and it's bounded above and below by negative constants. Questions on these statements?
No.
Sorry, Jonathan, I'm bothering you, but just want to make sure.
Do not worry with that.
So our theorems, of course, there's a gap between these two theorems. Anyway, neither of the theorems is sharp, unfortunately. So as I said before, there is a regularity gap in between these two conditions that I gave you. So for instance, what happens is the function is like x log x. In this case, this is in between sublinear and basically it's between Lipschitz and Euler. So this is something which is not taken care of in any of the two results. And here we don't know in general, but we have an example. So for instance, if we take this function, which is like x log x on the right, and it's plus infinity on the left, and it does whatever. I mean, we just care about basically this point. So we don't care too much what it does away from it. Then it's incomplete. So it means that the incompleteness condition is not sharp. But at the moment, we are not able to improve it much. And again, a sort of side comment, by a previous result of myself with Francesco Bonsante, we've been able to classify surfaces of curvature -1 which have bounded fundamental form. And this is stronger than completeness, basically because bounded second fundamental form tells you that the Gauss map is by Lipschitz to H2. And this is characterized by a certain regularity class, the Zygmunt class on the null support function, which is class which lies between Lipschitz and Euler. So this is sort of a related result, but on a more restrictive condition than complete. So an important thing is that with all these results, all these statements can be somehow localized. So we can give a notion. So far, I described your result that classifies complete surfaces. But in fact, I can interpret this in a fixed direction. So I will give you a notion of completeness in a direction P. So fix a point P of S1, I'll give you a notion of completeness in this direction. This is just the fact that basically there is no, so what's the definition? Let's take an entire surface, okay? We say that our surface is complete at this point if every Cauchy sequence that approaches a light-like plane corresponding to the direction given by P in the previous pictures is converging. So basically this means that there are no diverging Cauchy sequences that approach a light-like plane directed by the point P corresponding to the direction P, okay? And here approach means just with respect to any Euclidean. So I mean, when I say approach a plane, I mean for the Euclidean topology. So basically fix any scalar product on R3, and I'm saying that the sequence is approaching with respect to the Euclidean distance. So it's not it's in a very Euclidean sense. And let me also remark that it's possible that such a support plane does not exist. So basically, if in the direction P, the null support function is plus infinity, it means that there is no support plane of light-like type in this direction. And in this case, this definition is trivially satisfied. Okay, so is this clear?
Yes, I think so.
So in this case, if phi sigma of pi is plus infinity, then basically you're automatically completing in the direction P, because the definition is trivially satisfied. So all the theorems that I showed you before have a local version. So basically we can fix the point P, and our condition, now it's not for every P, we fix P, and this condition for this fixed P distance on a sequence on which the function is sublinear implies completeness at P. And the analogous for the other condition. And the fundamental lemma in this story is that if a surface sigma is complete at every point P, then it is complete. That's not completely true. It has to be proved. And also, as a last comment on my results, I want to give you a better understanding of the incompleteness. So what happens when the surface is incomplete? We are still able to characterize the induced metric. So our result is that whenever you have an entire surface which has constant curvature -1, then it is intrinsically isometric to the interior of a convex hull. So it's a picture like that. This is the Poincaré model of H2. Take any subset of the circle, take the hyperbolic convex hull. That's what an incomplete surface looks like. So special cases are, well, of course, H2 is a convex hull of the whole S1 in H2. So this includes complete surfaces. Also, the examples that you've seen before, the half plane is, the convex hull of a half circle. So, and now we can understand much better this, because basically all these boundary components that you see, all these boundary components you see in the completion, let's say, of the induced metric correspond to directions in which sigma is incomplete. There is a bijection between incomplete direction and these boundary components in the convex hull. So, for instance, this example here, this was the surface, this parabolic invariant surface, which was incomplete in just one direction when we had this jump. And this result is sharp, meaning that every region like that, every convex is realized as the induced metric on an entire surface. So this is complete characterization of what you see as the induced metrics. Good.
Nice.
And this result is also to bounded negative curvature. So basically, one can prove that the completion of the induced metric is somehow a surface with totally geodesic boundary. So when the curvature is bounded above and below by negative constants. And let me just make a remark on what happens. I mean, what might happen in higher dimensions. But it's very hard to generalize these results to higher dimension. So, well, one thing which is very easy is to show that the only hypersurfaces which have constant, of course, there are various notions of curvature that you can consider. If you just consider constant sectional curvature, then it's very rigid. You get only hyperboloids, and that's easy. Any hypersurface of constant sectional curvature in higher dimension is a subset of the hyperboloid, just as in the Euclidean case. One could consider instead the Gauss-Kronecker curvature. So consider basically the determinant of the shape operator to be constant. But here, even if we take a continuous null support function, there are counterexamples to the existence problem. So it's much harder. You cannot just assume that phi sigma is lower semi-continuous as in dimension 3. There are some positive results. So if phi sigma is moot, then there is the existence for Gauss-Kronecker curvature, and it is also complete. And that's basically what is known in higher dimension. There is also a very nice result by Graham-Schmidt in dimension 3+1, which is the analogous of the Barbeau-Begay for constant scalar curvature. So basically, he finds space-like surfaces which are invariant by any affine deformation of a hyperbolic trimanifold group, which have constant scalar curvature. And let me just say that every statement on the induced metric is very hard to prove, in my opinion. So it's 9:50. I have 2 more slides. What shall I do, Jonathan? I have no idea what's wrong with my time.
I think that you can.
If you want,
I think that you can.
Huh?
No, in my opinion, you can continue, and we can take later some time on the break.
It's not going to take more than 10 minutes, I guess. So.
Okay.
Thank you. I don't know for how long I stopped speaking before, so I have no idea. Anyway, thank you for this additional time. I'll just give you 2 slides which give an overview of some of the methods that are used here. So the first fundamental method is barriers. Barriers. What do I mean? We have one tool which is a comparison result, and it's the following. So basically, suppose we have 2 entire surfaces of curvature -1 as always, and we have the null support function. We have an inequality on the null support function, and they agree at one point. Okay, so then we can deduce that if sigma1 is complete, then also sigma2 is complete. Why is that heuristically? Because these 2 surfaces are asymptotic to the same light-like plane. But this inequality tells us that one is below the other. So basically, if the one which is closer to the light-like plane is complete, then the other one, which is above, is further. So it's a fortiori, it will be also complete. Basically, because the only way to be incomplete is to approach a light direction very, very quickly. So if one surface approaches the light direction less quickly than the other, and the other is complete, then also the former is complete. And this is used all the time. So for instance, using this comparison, one can prove that if there is a jump at one point, then the corresponding surface is incomplete. So let me give you a picture. Basically here, the red curve, we focus on this point here. So suppose we have 2 surfaces for which the null support function agree at this point, and the black one has a jump. Then you can use this one, which is the parabolic invariant surface, which is incomplete, and use it as a barrier, and deduce that also this blue one is incomplete. That's pretty easy. And that's how our incompleteness criterion goes. Basically, one does some more work to find an incomplete surface for which the null support function behaves like this, okay, for C and alpha arbitrary. And then our result follows, because basically this barrier tells us that this difference cannot be larger than C p minus p0 to the alpha in a neighborhood of the point p0, just because you use this explicit surface as a barrier. And this lemma. You can also use this lemma to prove something on the completeness. So for instance, if you use a simpler case than what we do in our theorem, but if you use the anonymized surface, then you can prove that if the function is Lipschitz, then the surface is complete. Here is the picture. Just remember, the anonymized surface had this null support function, piecewise affine. So if our surface has a Lipschitz null support function, then you can use this one as a barrier. And we know that the anonymized surface is complete, so you deduce that also your surface with Lipschitz null support function is complete. This is not completely surprising, because basically this result before that characterizes boundy's second fundamental form in terms of Zygmund regularity, and this is stronger than completeness, and Lipschitz in Zygmund. So it's not a proof, but it's somehow to say that Lipschitz implies complete, Lipschitz null support function implies completeness of the surface is not so surprising. But our result is better. Our result says that if you're just sublinear on a sequence, then the corresponding function is complete. And here comes the other method. The other method that we use is basically looking at asymptotic rays. So here is another fundamental lemma. So this says that, again, you have an entire surface of curvature -1. If it is incomplete, then you're going to find a finite length geodesic, which is asymptotic to a light-like ray. and the light-like ray is parallel. So if it's incomplete at the direction P, then the light-like ray is parallel to P1. So it's directed by this point P. So we have whenever you have incompleteness of the induced metric, finite length geodesic, which are asymptotic to a certain ray. And this is fundamental for two reasons. The first one is it's because it's thanks by this lemma we can prove that complete is the same as complete in all directions. So the first fundamental form is a complete metric if and only if the surface is complete in all directions, according to the definition before. But this is also the lemma which is used to improve to this condition. So remember, our theorem tells that if this condition is satisfied, then the surface sigma is complete. And here I'm going to sketch very, very quickly what is the idea. Basically, the idea is the following, that there is a compactness for entire surfaces of constant curvature -1. And the compactness tells the following thing, that basically if you have a sequence of entire surfaces of curvature -1, then suppose that they converge at one point, so they not escape far off at infinity, then these surfaces have a limit because up to subsequences, because these are graphs of Lipschitz functions. And the possible limits are either a light plane, so something degenerate, or basically a wedge bounded by two light half planes. So how to explain this? Basically a wedge region bounded, which is in the future of two half planes which intersect on a space-like line. So sort of this wedge, or an entire surface of curvature -1. These are all possible limits. Of course, here there are many, many things that can occur. But basically, light plane and wedge is the two degenerate thing. And if these are not limits, then the only possible limit up to a subsequence is an honest entire surface of curvature -1, a smooth one. And so basically, here I'm going very, very roughly, but this condition tells you that you can use linear isometries to take your surface sigma along a diverging Cauchy sequence and bring back this sequence to the origin, to the compact region of Minkowski space. And this condition tells you basically that the light plane and the wedge cannot occur as a limit. So the only possible limit is an honest entire surface of curvature -1. But this contradicts the fact that the Cauchy sequence was diverging, because, basically, it means that you have we had a finite length geodesic, and we use isometries to bring this to a finite region. So basically, this should diverge to something light-like, because the length of the geodesic was finite. So that's why this condition plus the lemma gives you the contradiction and implies the surface is necessarily complete. Okay, I'll stop here. Thank you very much for your attention, and sorry for the technical issue.